All right, I want to welcome everyone out this evening to the January edition of our Deep Talk series here at the Sanford Underground Research Facility. My name is Mike Ray. I'm the Media Relations Manager here at SURF. It's wonderful to see such a great turnout on what could be a much colder evening. It's not snowing yet, so that's wonderful. Glad to see you all here. Tonight we've got a real special talk, Into the Hearts of CASPAR, with Mark Into the Hearts of Stars with CASPAR, an experiment support scientist at Sanford Underground Research Facility. Mark Hanhardt, and a Ph.D. candidate at South Dakota Mines, is going to give this talk. I'm really excited about it. It's going to be a fun one to have. We also need to thank our sponsors, though, the folks who were able to provide us the wonderful beverages and the food. And so Deep Talks is made possible each month by Crow Peak Brewing Company, Edward Jones Financial Advisor Chris Mitchell, RCS Construction, and Charles and Jolene Lichtenwallner. So let's give our generous sponsors a round of applause and thank them for that. Without further ado, I'm going to turn it over to Mark, and I'll be back a little later for Q&A, so think of some good questions.
As Mike said, my name is Mark Hanhardt. I'm an experimental sports scientist at SURF and a Ph.D. candidate. Is it better? Okay. Got it. No, fair enough. Ended up creating the much more interesting universe. Is that not working? Right. I may just have to speak very loudly. No, we're better now? Okay. Hold it. Oh, that is very uncomfortable. All right. Well, it's the interplay of these atoms with the four forces of the fundamental universe that made this awkward moment right here possible. Without those forces, without the process that generated the elements and the galaxies, the stars, the planets that we have today, we wouldn't have any of this. So nuclear astrophysics is the field I'm in, and that is the study of how we went from there to here, to a much more interesting universe. And because it is really the study of the origin of the elements that make planet Earth and us possible, it's also the study of us, how we got here. So my goal tonight is to talk to you about CASPAR and explain to you some of the nuances of nuclear astrophysics, and in so doing, help everyone to understand why CASPAR is objectively the coolest experiment going on underground at SURF. There's some frowns among some dark matter scientists, I recognize. And fair enough, they've been embittered by years of jealousy over CASPAR. So let me put it this way. I will explain CASPAR and what we do, and I will let the audience come to their own conclusion about why CASPAR is the coolest experiment underground. So you can't tell the story of CASPAR without first of all talking about the story of the universe itself. And that's a story that starts a long, long time ago, 13.8 billion years ago, in fact. Everything that makes up the stuff in the universe around us, everything that makes up everything inside the universe that we observe today, was contained within a unimaginably energetic, infinitely dense point. So small that to even call it small is not quite correct. It was a mathematical point with 0 dimension. And that was what existed before the very first moment, what existed before the Big Bang. So, the Big Bang. A lot of stuff happened very quickly that was all very, very interesting. And I could literally fill an evening talking about all of the things that happened in the first picosecond of the universe, and I have. I'm going to skip most of that and skip to after all of the really big small things that happened. Big small things, I realize that's an oxymoron, but stick with me here. Because a lot of really big small things happened right after the moment of the Big Bang. So everything that happened before the first 10 to the negative 43 seconds, which is, I worked this out, 1/10,000,000th of a millionth 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 of a second. Everything that happened before that, we don't really have a grasp on in physics. We don't have the mathematical structure to be able to describe that. But the things that happened after that include the separation of the four forces of the universe into individual forces. Before that, they were one grand unified force. And those forces, for those of you who aren't in the know, are gravity, and we're all pretty familiar with that. The electromagnetic force, which really, that's the force that we as humans are probably most familiar with, because that's the force that, for instance, keeps me from falling through the podium when I push on it. It's what controls basically all interaction with normal matter as we know it. And then the strong nuclear force and the weak nuclear force that are a little more nuanced, and I won't get deeply into those. Among the things that happened just after the Big Bang, the expansion of space-time. The canvas on which reality is written started to expand, started to grow. And in that early universe, there was a lot of energy, a lot of heat, and not yet matter, rather. Within that first picosecond, we then had the creation of all the mass that exists in the universe today. And that involves quarks. Those are the constituent particles that make up the normal matter we're used to, the protons and the neutrons, and the leptons, which are the electrons and the neutrinos that occupy the universe. On top of that, we also had the introduction of mass. Before the first roughly 10 to the negative 20th of a second, there was no mass in the universe. Even when there was matter, there was not yet mass. Mass had to be something that was assigned to matter later on. And that's all that happened in the very first, really short period of the beginning. We're going to fast forward all the way to the first 10 seconds after the beginning of the universe. That's where the nuclear astrophysics really starts. This is when what we call the Big Bang nucleosynthesis began. So the universe was very small, very hot, very energetic, and filled with a lot of new types of mass, including these quarks that I mentioned before. About 10 seconds after the Big Bang, the universe had spread out enough, it had become big enough, and the energy density had dropped enough that the quarks, which were kept from forming into bigger particles before then, became the first nucleons. They became the first protons and neutrons. And then, as the universe continued to expand and the energy density continued to drop, those first nucleons formed the very first nuclei. So they formed hydrogen and helium nuclei. A hydrogen nucleus is just a proton, so it feels like cheating, really, to say that those were formed, because we had protons around. Helium nuclei consist of 2 protons and 2 neutrons. So in the places where that was possible, those things formed, and after the first 17 minutes, I know that already seems like a really long time after the Big Bang, but after the first 17 minutes, we then had a lot of hydrogen and a lot of helium nuclei. We didn't have atoms yet, but we did have the nuclei. And the universe was about 25% of this helium and 75% of this hydrogen, and really not a lot else. A handful of lithium atoms here and there, but that was really it. So now we have the major players in the story of the universe. We have energy, and we have the nuclei of the atoms, and then we have electrons filling up the universe. That's when the universe starts what's called the photon epoch. Everything after 17 minutes, all the way to 380,000 years after the Big Bang. And I realize that's a big time step. But that entire era is called the photon epoch, and the entire universe, which was still quite small and still quite energetic, was filled with plasma. Plasma is the protons and neutrons, it's the nuclei that I spoke about before, and the electrons, but none of them bound together in atoms. So it was this glowing, super hot gas. When I say glowing, I mean that this gas was constantly emitting and absorbing photons, but those photons couldn't go very far because the universe was so dense and it was so energetic, and the electrons that were not yet bound to the nucleons were immediately absorbed. So the universe was simultaneously filled with light and completely dark. So if you were in the universe at the time, you wouldn't be able to see anything because photons couldn't travel very far before they were immediately absorbed again. You would also immediately melt because it was 6,700 degrees Fahrenheit. My sister, when I ran this by her earlier, said that would at least it'd be the first time she ever felt warm. An exciting part of the universe if you're always cold, otherwise not a great place to travel. That was the photon epoch. Shortly after that, between 380,000 and 480,000 years after the Big Bang, we entered the recombination period of the universe. And this is, those of you who heard me speak about this sort of thing before know that I absolutely hate this name. This is the worst named thing in all of physics, recombination. I'll explain this. What happened was, as the universe continued to expand, the energy density dropped low enough that these electrons that were previously in this giant plasma soup that couldn't latch on to the nuclei and create the first atoms, finally were able to latch on to those nuclei. We had the creation of the first actual hydrogen atoms and the first helium atoms when those electrons latched onto those nuclei. And that's called recombination because, of course, we finally had the combination of the nuclei and the electrons together. That's combination. That's not recombination. You don't get recombination if it's the first time it's ever happened in the entire universe. Physicists are awful at naming things. But still, the name recombination sticks. And this was the point at which the universe saw the very first atoms. So during that 100,000 year period, this is the birth of the very first atoms in the entire universe. And that's the hydrogen and the helium. Again, that ratio sticks around. We have about 75% of all the baryonic matter like this in the universe is hydrogen, and 25% of it is helium. What's really interesting for me, well, there's a lot of things interesting to me about this period. Perhaps the most interesting thing in all of science for me is what happened to the light that had been bouncing around, constantly being emitted and reabsorbed during this period, was finally free. When those electrons fell into the orbits around the atoms, they stopped absorbing those electrons, and this light that had been bouncing around since the very beginning of time was finally free to travel forward, and it created what we now call the cosmic microwave background. What had happened is that light was suddenly free, coming from, going in every direction rather, and coming from every direction. The universe, as it continued to expand over the course of the next 500,000 years or so, stretched out the wavelength of those photons that were traveling through space-time at the time to the point where they became invisible. And as space-time continues to expand now, it continues to stretch that out. So these photons that came from the birth of the very first atoms in the universe are still around us. If we look out in space, these photons are coming at us from every direction, in every direction, and they are a signal from this period in the universe. But because they've been stretched out, their wavelengths have been so stretched out, they're invisible to the naked eye, and you can only pick them up in microwave. That's why we call this the cosmic microwave background. This is a picture of what was picked up by the COBE satellite in 2008, 2005, but some time ago. This is a picture of space around Earth in every single direction, the cosmic microwave background that we've picked up from that. So this right here is those photons coming to us from the very early universe. This is a symphony being sung to us by the universe about the very birth of the very first atoms. And it tells us all sorts of things about what happened before, and it tells us all sorts of things about what will continue to happen in the universe. It's an incredibly useful bit of scientific information, this cosmic microwave background, and it's my single favorite topic in all of science. Again, I could waste an entire evening talking about this, and again, I have. But we'll try to skip ahead and go on to more nuclear astrophysics topics. recombination period, we have that cosmic microwave background, and at first would have been all visible light, so the universe would have been filled with visible light. But after 500,000 years, so about 1 million years after the universe had been born in the Big Bang, that light had already been stretched out to the point where it was invisible, and the universe entered a dark age. So had you been around in the universe at this point, it would have been dark again, nothing to see. You wouldn't probably have melted, but there's no oxygen, so it still wouldn't have been a great place to be. So for about 150 million years, the universe is completely dark. The universe has continued to expand, the energy density is continuing to drop, and we have vast clouds of hydrogen and helium not really doing much until the reionization period. So about 150 million years after the birth of the universe, these vast clouds of hydrogen and helium started to form, which was mostly uniform throughout the universe, started to form around certain centers of slightly higher density. When a bit of gas has a slightly higher density than anything around it, it has slightly more gravitational pull than anything around it, and that means it's going to start pulling in more gas. That means it's going to have more gravitational pull, which means it's going to bring in even more gas. And you get this cascading effect where any area that was just slightly denser than the uniformity before it is now the center of this, giant ball of gas that's continuing to collect and heat up. And this is a period we call reionization, because the hydrogen atoms, the helium atoms, start bouncing around with enough heat, with enough kinetic energy that they're knocking off their electrons and becoming a plasma again. This one's properly named, by the way, reionization. This is the second time these gases have been ionized, so well done, physicists. This took a long, long time. This is a very, very slow process throughout the universe. About 1 billion years after the birth of the universe, we finally move on for reionization to the next step, which is the stelliferous era. What happened is the centers of some of these giant clouds of gas, the ionization in the middle, became hot enough that the atoms there were able to undergo the very first nuclear fusion that we saw in the universe. And that's the birth of the very first stars. So about 1 billion years after the Big Bang, we finally see the birth of the first stars. And that's what defines the stelliferous era. The stelliferous era, by the way, is the era of the universe in which we live. So it's the era in which I was born, which means it's the most important era in the universe. Best so far, anyway. As those giant clouds of gas, as I mentioned, continued to collapse in on each other, the center of them became hot enough to undergo nuclear fusion, and we had the birth of the first stars. We had the first light, then again, in the universe in 850 million years. So the universe finally had something to see. So again, if you're sightseeing, this is the time to go to. It's worth talking about what actually takes place inside of a star during the fusion that I mentioned. So it takes quite a bit of energy to get helium to fuse. So that's not the first thing that happens. When these giant balls of gas come together, we actually start with hydrogen burning. We start with hydrogen fusion. And this is a fairly straightforward process, but it does have multiple steps. Basically, these hydrogen nuclei, which again is cheating, those are just protons. When these protons come together with enough force, they can actually create a deuterium nucleus. What happens is one proton and one proton come together with enough force that one of them then becomes a neutron by shedding an electron, and then you have a deuterium atom that fuses with another hydrogen atom. It creates, as you can see in the chart here, it creates a helium-3 atom. You get that to happen twice. Those two helium-3 atoms can then form a helium-4 atom, releasing two of those protons back into the system. And this is a process that continues on. And what's probably most important to point out is that while this process is taking place, it's releasing energy at every step along the way. If you can see at these sections, you can see it's shooting out these, what looks like a Y. It's the Greek letter gamma for the gamma rays that it's outputting. And that energy stored in the gamma rays continues to heat up the core of that ball of gas, the core of that star. That energy then allows the star to burn. This is what's happening in the very first stars. And this is, in fact, the process that takes place inside of our star. And I suppose this isn't the point of this, but it's worth pointing out that the other products of this are these neutrinos, rather, that come out of this. So if you've paid attention to the other deep talks, you've probably heard about neutrinos. This is the source of most of the neutrinos that we see on Earth coming from the sun, from this process right here. If you were to hold out your hand at any point on Earth, you have about 16 trillion neutrinos going through your hand every second just from these processes taking place in the sun. So this is a pretty important nuclear reaction. As it's producing all that energy is heating up the core of the star, which is then pushing back on the gravitational collapse of that giant cloud of gas, and in such a way that it creates what we call hydrostatic equilibrium. That's basically what keeps the star from continuing to collapse. So once you have a star, once you have a ball of gas that is undergoing fusion like this, that is generating enough energy to keep itself from continuing to collapse, that's a star. So this is the birth of the very first stars in the universe. What happens next depends entirely on the mass of the star. Basically, the entire life cycle of a star is determined by how much mass exists in the clouds of gas that formed it in the first place. Over time, once you're done burning all the hydrogen in the core of a star, if you have enough gas, which is to say, if there's enough gravitational force to then continue to crush the star so that the center becomes hot enough to burn helium, you can then continue on to the next step. But if you don't have enough mass, then you're done burning hydrogen and your life as a star is near an end. You become a white dwarf, and then you spend the rest of your trillions of years just being a white dwarf until you run out of whatever fuel allows you to continue that. And then you're just a husk of a star floating deep in space. I didn't mean for this to get so depressing when I started that sentence. It just went on there. I want to talk about the more exciting ones, though, of course. The stars that have enough mass, then when they're done with hydrogen burning in the core, they're able to undergo helium burning. Helium burning, it requires a lot more energy. So what happens is you're done hydrogen burning. You're no longer putting out that energy that keeps the star from collapsing, so the star starts to collapse again. And in so doing, the center of the core gets hotter and hotter, and you reach the energy then when helium is able to burn. Helium burns a lot hotter, so the outer layers become more diffuse. They spread out more, so it becomes a red giant, a much, much bigger star with a much, much hotter core. And that helium burning looks something like this. I'm not going to walk through all the steps of all the reactions that we've done. Just worth mentioning, it's kind of analogous to the hydrogen fusion I mentioned before, but rather than hydrogen turning into more helium, in this case you now got helium turning into carbon. And there are other processes that aren't shown here, but you can also generate oxygen and calcium and other processes in this stage. So if you've got helium burning going on, once you're done with helium burning, that same process happens. The star loses the ability to hold itself up, it starts collapsing again, and the center gets hotter and hotter. If you have the mass then, you're able to start burning carbon and oxygen into heavier things. And then the same process again. You run out of energy holding the star up, you start to collapse, and then you need energy to go on to the next cycle. So it's that over and over again. The entire life cycle of the star, as I mentioned, is determined by the mass of the star at the beginning. So you can see kind of a cycle here for the way things can go for a star. We're interested in the heaviest stars, the ones that are able to actually go through all of these processes. So hydrogen burning at the beginning, helium burning, then carbon and oxygen burning, then I want to say calcium burning, and then actually I'm going to flip to the next slide because it's written down. I don't have to remember this. Carbon burning, neon burning, oxygen burning, silicon burning, iron burning. So this is a process that happens over and over again in the heaviest stars. And in the heaviest stars, it happens very, very quickly. Because when they're really heavy, there's a lot of force in the center, a lot of force crushing the star together. So the center of the star is hotter and hotter. The hotter it is, the quicker it burns. You get to a point where you've burned hydrogen, which generated energy, which held up the star. You've done the same with helium. You've done the same with all the steps along until you reach iron. And then there's this weird thing that happens in nuclear physics. Because when you start trying to fuse iron into heavier things, it doesn't work. Well, it does work, but you don't get a lot of energy out of it. In fact, you don't get any energy out of it. You have to put energy into it. So this subtle balance between the gravitational force inward, making things hotter, and the fusion trying to hold the star up, keeping it from collapsing, suddenly has no energy to try to keep the star from collapsing. So when you've gotten to the point where you start burning iron, you're now sucking energy out of the system, and the entire star collapses. And that leads to what we call a supernova explosion. So we started with a ball of gas that was mostly hydrogen, a little bit helium, and we've ended up with a ball of gas that is a lot of hydrogen still and a lot of helium, but also now other elements, carbon, oxygen, nitrogen, silicon, iron, and a temper and not a lot of will to live. So as these stars start to collapse, they start by shedding their outer layers and shedding mostly hydrogen and helium again into the universe, but the core collapses because it no longer has the energy to keep it up. And when it does collapse, it bounces and creates a supernova explosion that tears the star apart. And it takes all those elements that created over the course of its 100 million year life and spreads those ashes out into the universe. And those ashes then form into new stars. These stars are different from the first generation stars because instead of just having hydrogen and helium, they also have these additional atoms, these additional nuclei rather. And that makes other processes possible. And I'm not going to go through those, but what's more interesting, I think, from our perspective as humans, is that the clouds of gas now have carbon, oxygen, nitrogen, silicon, all those things I mentioned in them. And we can now, as we start forming new stars, also form rocky planetary bodies. You can form stuff like Earth. I say you, as if any of us are creating stars in our spare time, but the universe has the ability now to create rocky planets like Earth. And that's in fact how our solar system was formed. We are the result of the ashes of several generations of stars that formed, burned out of their elements very, very quickly, exploded, spread their ashes into the universe, and then eventually became us. So every single atom on Earth has its origins somewhere in the stars. The carbon, the oxygen, the nitrogen, I know I keep saying those three, but those are the most abundant, at least in life. The atoms in your body, the things that you can actually touch, the things that you can feel, they came from the heart of a star, the 100 million degree furnace at the center of a star that eventually exploded and then formed over the course of billions and billions of years into us. So every rock, every tree, every drop of water, and you and me, I didn't intend for that to rhyme, that just worked out really well for me, came from the center of a star. Carl Sagan used to say, we're made of star stuff. And this is exactly what he was talking about. This is the process that really generates us. So nuclear astrophysics helps us understand this roadmap from the beginning of the universe to here. And it really is us understanding our chemical lineage, how humans came about. So that's the story so far from the Big Bang to now. Telling it from the kind of stars point of view. Real quick, just to take a look at the element point of view, I want to look at that side of things. It's worth mentioning it first. So these are two pie charts that show the elemental abundance at the very early stages of the universe. I realize the text is really small. I need to blow that up. But the early universe was about 75% hydrogen and 25% helium. And after 13.8 billion years of this cycle of stars turning hydrogen into helium, helium into heavier elements, and exploding and spreading those ashes into stars, 13.8 billion years of that happening, we're now at a point where the universe consists of 74% hydrogen, 24% helium, and that 2% is everything else. And that's us, and that's Earth. We're all made of that 2% of the atoms that are not hydrogen and helium in the universe. A lot of progress made. This is a periodic table of the elements. I probably don't need to point that out. You guys probably recognize this. It's worth talking about this because so far I've told you how the universe generates all the atoms up to iron. There. There's a lot more than iron on that chart, as you can tell. So how did the universe pull that off? Well, there are other processes that are required to create other things in the universe. The supernova explosions that I mentioned, those are energetic enough that they can actually create a lot of the things that are heavier than iron. It doesn't create more energy, so it's not sustainable. It has to happen very quickly, and it has to happen in small proportion compared to the other elements that are created. But that's how we get heavier stuff like platinum. There are even more exotic processes that happen to create other things. For instance, when super, super heavy stars die, they undergo that supernova explosion. Sometimes there's a bit of a core left over that is so heavy, so dense, that the atoms themselves are crushed out of existence and they become what's called a neutron star, a star made out of just neutrons. When two of those neutron stars collide with each other, it is one of the most energetic events in the entire universe. That's called a kilonova, because again, physicists are just awful at naming things. When a kilonova happens, we finally have the energy required to create gold in its elemental form. So all the gold on Earth, again, formed from the ashes in the cosmos, and in the case of that particular atom, came from a kilonova. The merger feels, it's not a violent enough word to describe what's happening. The collision of two neutron stars together is how we get those atoms. So we have to tell, nuclear astrophysics is really very much about telling the story of how we got all of the other elements after iron. Because the story up to iron is, don't get me wrong, very fascinating, but ultimately not as interesting as the stuff beyond that. So that's one of the major goals in nuclear astrophysics, understanding where these atoms come from in the first place. Because even though you probably don't deal with technetium much every day, without it in place, we don't get the universe that we have today. So every one of those is important, and the story of how we got there is important. So just real quick, this is a periodic table of elements. I don't know if you can read it at the bottom. I didn't mean to include that, but I wrote for wimpy chemists. That was from a previous talk, and I forgot to erase it. This, however, come on, is the chart of nuclides. This is what physicists use, which, as you can see from the subtitle I've described, is unstable, and that's fairly accurate. This is a chart of nuclides. So the periodic table of elements has 118, I think, elements. This version has, 118 elements. The chart of nuclides currently has 4,040 boxes in that little chart. That's all of the elements plus all of the isotopes. So this is what we work from. And I only point it out because I like to mock the chemists to, show that what we're dealing with is a lot harder. And I've spent enough time with this that, as I've mentioned to people before, if you can see each one of these boxes actually has quite a bit of information in it. And I've spent enough time with that chart that if you were to point out any single box on there and ask me any of the numbers in there, I will immediately start crying. It's very traumatic. That's the chart of nuclides. So I mentioned some of those other processes. About half of all the elements beyond iron on the periodic table are created in the R process, which is the rapid neutron collection process. Rapid neutron accumulation process, rather. Again, physicists and naming things, R process. Those are the things like supernova explosions and kilonova, those collisions of neutron stars that I mentioned. So about half of all the elements, heavier than iron, are created that way. About half of all the other elements are about half of the elements, I'm trying to state this in a way that is mathematically followable. The other half are created via what's called the S process. There are a couple of things here and there that are created via some really exotic processes that are not R process or S process. But mostly the R process and the S process describe everything that's not iron. The S process, you'll never guess if R is the rapid process, is the slow process. S process. That's a process that's just this slow accumulation of neutrons to atoms over time, and then them decaying into different types of atoms. So about half the atoms after iron are explained via that. And there's some really mysterious processes that go along that make the S process work. And that's a big part of what we study in CASPAR. It's not the only thing we study, but it's a big part of what we're trying to kind of unravel with CASPAR. So that's the element side of things. I'm going to introduce you now to CASPAR. So again, you can see why it's the coolest experiment underground. First of all, you probably know this already, having come here, but we're an experiment at the Sanford Underground Research Facility. We're about a mile underground at the Ross campus on the 4850 level. If you have a chance to look at the model, we're on the copper colored level down here, and we're about a kilometer away from the Davis campus, which is where the LZ experiment and the Majorana experiment are. So CASPAR stands for the Compact Accelerator System for Performing Astrophysical Research, which is a real stretch of an acronym, but I like it, it's stuck. We're a we're a small particle accelerator designed for recreating nuclear reactions that take place inside of stars so that we can watch them up close and try to understand what they do. Observe things that would otherwise be obscured to us in the stars because it's really hard to look through a giant ball of gas that's on fire. So the core elements of CASPAR, I'll run through these fairly quickly. But the accelerator. CASPAR is itself an accelerator. We're designed to smash things into other things, which is just my favorite kind of physics. Our goal is to accelerate subatomic particles and then ram them into other atoms to undergo nuclear fusion so that we can watch that. The way that we do that is with the accelerator system, and the biggest part of the accelerator system is what we call the accelerator itself. That's the part that you basically load up with atoms and shoot them. So if an accelerator system is a gun, this is the chamber. This is the part you load up with particles to then shoot down the beamline and shoot at other things. One of the major components we can't live without is what we call the ion source. So just as the universe uses gravity to crush a lot of gas into a space and ionize it so that those atoms, those nuclei rather, can undergo nuclear fusion, we use our ion source. It's a glass bottle that has a magnetic containment field inside of it. We fill it up with either hydrogen or helium gas that we buy locally, and then we subject it to a really strong radio frequency, strong enough that it strips off some of the electrons, and that turns it into a plasma. And that's what's glowing purple there. So this is kind of our version, this is our way to mimic the way that the universe creates plasma in the center of a star. We're kind of cheating the universe and creating it without having to put it in the ball of the center of a giant ball of gas. We also have targets that we shoot those particles at, and they're not as complicated as you would think. As you can see, that's me holding one right there. It's about the size of a 50-cent piece, and it's just a chunk of tantalum foil, which is a lot like aluminum foil, but more sciencey and expensive. And we coat it in an atom that we're trying to study. This one right here is covered in lithium-7 atoms, which is something I used for the data I collected for my Ph.D. thesis. And you can actually see where we've already used it. We've shot the particle beam at that section right there, where it's undergone nuclear fusion and worn away the lithium-7 atoms. So that's what a target looks like. Here's what a detector looks like, and this is one of my favorite bits of equipment in the world. So the accelerator is at that end. It shoots the particles all the way through the beamline, and then at a target, which is in the center of that detector right there. And I love this because not only does it look like a prop from a 1960s sci-fi film about an apocalypse machine, but this detector is what actually allows us to view the nuclear fusions that are happening inside of our target. all of these devices on top are photomultiplier tubes that are very similar to the ones that were used in LOX and are currently being used in LZ, and you can actually see display. Is it hidden behind the TV there? Yeah, behind the TV there we have a photomultiplier tube you can actually take a look at, and that helps us look inside the nuclear reactions we have going on. So inside of that detector, we actually have, on the surface of that target, nuclear fusion going on. We're basically recreating the heart of a star inside of that tiny chamber there, a mile underground. So we're currently in the process of restarting CASPAR. We had to mothball it for a while so that we were not in the way when they were excavating for the DUNE experiment that's coming up, big neutrino experiment that's coming up. For some reason, they didn't want scientists running nuclear experiments while explosions were going off all around. Sounds like fun to me, but you know, insurance wouldn't cover it. So we're currently in the process of restarting CASPAR. We've spent the last year and a half cleaning up the old lab and getting all the equipment ready to go. You can see a picture here of some of the Notre Dame scientists working to put all of the stuff back together. We had taken out all of the really sensitive stuff before the explosions, as you can imagine. And just in the last few months, we have hit several milestones, including reigniting that plasma. I'd shown before that kind of purple glowing bottle. That was our ion source. In this picture, it appears a little more red because we're using a different type of gas. But this was us reigniting our plasma for the first time. This is, of course, the picture that SURF published. This is the one they won't. I don't know what else I can say. Dan has real nice eyes. It was good to spend that time with him. And then more recently, just about a month and a half ago, no, not even that, just a month ago, we finally generated particle beam that we were able to put on a target at the very end of our experiment. And that's what you see in that glowing blue square there. That's an actual particle beam hitting the target where we've replaced, instead of having that tantalum foil with atoms spread all over it, we have a quartz window that glows when we have a proton beam on it, and that helps us figure out where that beam is inside the beam line and helps us know if we need to realign things, which we do. And this was a big milestone for us because we finally got particle beam to the end of the system. So that's getting CASPAR started. And I probably should have said this before. I didn't mention this at the beginning, but CASPAR is an experiment run jointly by the South Dakota School of Mines and Technology in Rapid City and the University of Notre Dame in Indiana. There's between 12 and 20 of us working on the experiment at any given time. Most not on site, most working off site to get analysis done and prepare stuff like targets and prepare technology for us. And then the on-site crew is typically between 3 and 6 people when we're actually running, and we're looking forward to getting things running again. So I recognize I'm already running near the end of my time, so I'll probably skip most of the nuclear physics lesson and possibly the quiz. We'll see how good you are. But you may ask if we know all of the stuff that I've talked about so far about the formation of stars, about the formation of elements, why do we still need to do CASPAR? There's still a lot of other mysteries out there, things that we don't understand, and a lot of reactions that we need to understand better. And that's because the reactions aren't as straightforward as you would think. And maybe it's stupid to say, but nuclear physics is kind of hard. There's a lot of nuance to it. And one of the things that makes it a little difficult is something called nuclear resonance. And you know what, I think I'm just going to mention this and then not explain it fully because I think that'll be maddening for people and that amuses me. One of the weird things about nuclear physics and quantum physics is that things aren't as straightforward as you would think. If you throw one atom really hard at another atom, you would expect that as long as your aim is right, they would hit each other and they would fuse as long as you've given it enough energy. That's not quite the case. Even if your aim is perfect, those particles might just pass through each other, just due to quantum effects, just due to the quantum nature of the universe. Those particles might pass through each other. And if you give it a little bit more energy, then they might stick. But if you get it more energy than that, they'll pass through each other again. for some reason, the reason is quantum physics. For some reason, things just on that scale don't act like you would expect them to. Things don't have the same physical corporeality you would expect. Things are able to just pass through each other. And the effect of that is something we call nuclear resonances. This is the data I was working on for the lithium-7 stuff. This is just to show you that if I throw an alpha particle at, an alpha particle, by the way, is a helium nucleus. It's a helium atom, and you've stripped the electrons off. We call it an alpha particle because it makes us feel big to come up with words that we don't think anyone else knows what we're talking about. If you throw an alpha particle at a lithium-7 atom with about this much energy, and I don't have it labeled there well, but about 400 kiloelectron volts of energy, you can pretty reliably make those things interact. You can pretty reliably get a fusion reaction. But if you give it just a little bit more energy, it stops reacting entirely. And then you give it a bit more, it starts reacting again. More again, it stops. More again, it picks up. That's called a nuclear resonance. And there's a lot of resonances with a lot of different reactions in nuclear astrophysics. And we can't really understand how the stars burn very well without understanding those resonances. So for the tens of thousands of different reactions that can happen, we need to understand these resonances well. And that's one of the reasons we have to continue doing work on CASPAR to fully flesh these things out. I'll explain this one fairly quickly as well. One of the reasons that CASPAR is so important to nuclear astrophysics is because of something called the Gamow window. Inside of a star, the particles inside the core of a star are they're hot. They're moving around a lot. They're bouncing around, and they undergo nuclear fusion depending on this factor called quantum tunneling. For years and years, since the birth of nuclear astrophysics as a field, we've tried to recreate a lot of those reactions on the surface using accelerators like CASPAR, but we've been unable to do so because we can't get low enough in energy without the results being completely washed out by the cosmic ray background. So for 70 years, people have done experiments and said, well, this is what it looks like at higher energy, and then extrapolate down, this is probably what it'll look like inside of a star. But we can't really do that well because those resonances are hard to calculate. They're hard to predict. So the only way to actually understand what happens inside of a real star is to go somewhere where you can actually conduct the experiment at the same energy that it takes place inside of a star in the real universe. And that's what CASPAR does. We're one of the first experiments in human history to be able to recreate these experiments at the same energy that they take place inside of a star. And that's called the Gamow window. So that's why CASPAR is so unique and so important in the world, because we're one of only 2 experiments in the world who can do the exact experiments we do. We're only one of 3 that does even this type of experiment at all. So the type of data we're doing here, really, you can't do it many other places. And that's why CASPAR is important. I suppose I stepped on this already, but the reason we have to do CASPAR is because there's still a lot we don't understand. Despite the fairly complete picture we have of how we got from the beginning of the universe to now, and how we will go from now to the end of the universe, there's still a lot of other stuff we need to figure out, including these mysteries I talked about, and a lot of bottleneck reactions and refinements to things that we think we understand fairly well so far. So that's the purpose of CASPAR. So I've prepared a final chapter. This is not CASPAR related, but I recognize that I've mentioned the beginning of the universe and how we've gotten to here from 13.8 billion years ago, and it feels like cheating to discuss that without then talking about what's after now. So I'll go through this fairly quickly, but this is going to get depressing. The end of the universe is kind of rough for a lot of people to take, so strap in. So we're currently in the stelliferous era. Like I mentioned, that started about 1 billion years after the Big Bang and has gone until now, which is 13.8 billion years after the Big Bang. It should continue for quite a while. The stelliferous era, by the way, is defined by the era in which stars are created. So as long as stars continue to be born out of the ashes of old stars, we will be in the stelliferous era. That may continue for another 100 billion years. It may continue for another 100 trillion years, somewhere in that range. We're not really sure because we don't understand the life cycles of stars as well as we would need to in order to nail this down. That's one of the reasons that the work at CASPAR is important, because it'll help us nail this down, and then we'll know, do we have 100 trillion years to waste, or should we not even, worry about exercise and diet if we've only got 100 billion years left? So at some point in the next 100 billion or 100 trillion years, the stelliferous era will end. The last star will be born. Now, the last star that is born, or a lot of the stars that are born along the way, are very slow burning, very low mass stars that will themselves last for 100 trillion years. So we will eventually enter an era called the nucleon decay, or the degenerate and nucleon decay era, during which there will probably be a lot of really low mass stars continuing to burn for a while. They will burn out during this period eventually. This era will be, it'll be mostly characterized by the carbon-oxygen cores of dead stars. Stars that were able to burn hydrogen, and then they were able to burn helium, but they lacked the mass to get any further. They never underwent supernova explosion, so they're just these giant balls of mostly carbon, a little bit of oxygen, that slowly, over time, have organized themselves into giant diamonds. Literal diamonds, giant carbon matrices, giant carbon crystals. So giant diamonds floating through a mostly dark universe. Which feels like a really metal thing to say. But this era will also be defined by the fact that the protons and the neutrons that make up the carbon atoms and whatever other remnants are left in the universe will slowly decay away, if our understanding of those particles is correct. So eventually, even those giant diamond stars will disappear, and we will enter the black hole era. The only matter left in the universe compressed into the final black holes. Those generate some light as long as there's an accretion disk around them, but because most of the matter will have been already decayed away or sucked into a black hole, no light coming from these either. Over time, the black holes themselves will decay away via something called Hawking radiation, and there won't even be black holes left when we enter the dark era. We have no idea how far away this is in time. We just know that it's a very, very big number. And that's an era that's defined by really not a lot happening. Nothing, really, because there's no matter left. And the universe at that point has expanded so much that all of the energy left in the universe, which is in the form of photons, has stretched out to the point where it's entirely unobservable. So, happy times. So that leads us to what the ultimate fate of the universe would be. And there's a lot of different theories out there. I'm going to cover some of the most popular ones. And the first of them is the heat death of the universe, what some astronomers have called the big freeze. We've already covered. I don't think that physicists or astronomers are really good at naming things. These names I like, because we've already gone from the Big Bang, the beginning of the universe. This is the counter to that. Basically, this is the idea that the universe will continue to expand, but slowly, and because there's no real matter left, and all the energy in the universe is already stretched out to nothingness. At this point, nothing will ever happen again. Heat death of the universe, big freeze. Not a lot to talk about there. One of the other ideas is that we may actually we may deal with something called a big crunch. It's possible that the expansion of the universe that's been happening since the Big Bang may eventually slow down and reverse. And it may actually bring all of space-time back together, and this may happen before all the matter is decayed. So this could happen in a universe filled with matter, where we basically undergo the Big Bang in reverse, everything being crushed down into a single point again, which sounds painful, but I don't expect we'll be around for it. There are ideas that this big crunch would then be followed by a second Big Bang, which they've dubbed the Big Bounce. I love the naming of these. Which would just be a creation then of a universe very much like this one, or at least in the very same method. So big crunch, big bounce. One of the other ideas is called the Big Rip. I like this one too, the idea that space-time, which is expanding and currently accelerating in its expansion, may never slow down, and in fact may continue getting faster and faster, to the point where eventually the fabric of space-time itself rips apart, rendering reality non-existent. I can't even begin to tell you what that would look like, so this is just an image I pulled offline of an oil spill. Couldn't think of anything else. But yeah, the idea that reality itself might just tear itself asunder and nothing ever will exist again. And then the last, the last possible ultimate fate of the universe is called the false vacuum collapse. And this is perhaps the scariest one, and I want to leave you with this one because if you can't leave them wanting more, at least leave them terrified and sobbing. The idea is that the universe as it exists today, and this is getting all quantum-y, so I'll skip most of this. The universe as it exists today exists in a false elevated energy state called a false vacuum. The idea that the very fundamental level of the universe has just slightly more energy than it should or than it could, that it could drop to a lower energy level. Kind of like if you were to roll a ball down a hill and then it gets stuck in a little divot before it gets all the way to the bottom of the hill. It's stuck there, but if you were able to get enough energy to just get it out of that little divot, it would roll all the way to the bottom of the hill. The idea is that the universe exists in that little divot, and we're just waiting for a little push to get over that hump and then into oblivion. And that's called the false vacuum collapse. And what's most terrifying about this is that, first of all, you shouldn't worry about this at night. This is really unlikely. But if it did happen, there's nothing saying that it couldn't happen now. If anything, anywhere in the universe is able to tip over part of the universe over that little dip into true vacuum, then that effect would spread out at the speed of light from there until it encompassed the entire universe. So it may have happened already somewhere several light years away and is just waiting to catch up to us. And what would happen in that case is very much like the Big Rip. Space-time would just kind of cease to be in its current form. So it's hard to even say what would happen to us. It wouldn't be survivable or probably very fun. But you wouldn't see it coming, so don't worry about it. So that's, I had to go into the ultimate fate of the universe because, you can't talk about the beginning of the universe without talking about the end of it. But that's CASPAR in a nutshell. We're looking to try to understand that roadmap from how we got from an early universe filled with hydrogen and helium to one that is much more exciting, much more rich, and has me in it. So thank you for listening, and I appreciate your time tonight, and I'm happy to answer any questions you have.
We're just going to get some microphones worked out here. Yep. Okay, we'll run with this real quickly, and we'll just go back and forth. We do have a little bit of time for questions. We broadcast this over the internet, so we want to make sure that this microphone is also being broadcast to the folks who want to listen out there. We had some viewers tonight. What questions do you have for Mark after this wonderful presentation? Who might have a question out there that this brought up?
Way back to the Big Bang again. You said helium, hydrogen, and lithium. And you kind of said, yeah, the lithium was there. Where did the lithium come from? And if the lithium wouldn't have been there, this wouldn't have gone the way it did, right?
We're still good on this? Okay, that's a fantastic question. When I said there's a handful of lithium, I meant a really, really small amount. It would have been 75% hydrogen, 25% helium, and like 0.000, repeat that about 10, 15 times, 0.1% of lithium. So very, very little lithium. And even if it had been slightly more than that, it wouldn't have changed things terribly much because it requires so much more energy to fuse lithium than it does hydrogen or helium that it wouldn't really have affected the way stars formed at all. But it's a source of a lot of mystery in nuclear astrophysics right now, because there are the math that we have for describing how lithium came about and what should have happened to that lithium over the course of the last 13.8 billion years does not match with the amount of lithium that we now observe in the universe. So there is this ongoing lithium problem that we're actually, CASPAR is part of trying to solve that problem. But I can tell you that even if there had been slightly more lithium, it wouldn't have affected the ultimate evolution of the universe terribly, terribly much. Oh, had there been less? You know, I don't know. I'm willing to admit I don't know enough about its role in the evolution of stars to know for certain that it wouldn't have caused a problem, but I don't, off the top of my head, I don't think it would have. Because ultimately, the tiny amount of lithium that did exist at the time was basically just an observer to everything that happened after that. It didn't play much of an active part at all. That's a good question, though. I'm going to have to hit the books and actually make sure I understand that correctly. That's a good question.
What other questions might be out there? Any others tonight? Might have sparked up? Yeah, please.
Doesn't the James Webb Space Telescope looking back into the dark ages, and now we're starting to see evidences of stars, galaxies, and stuff like that being formed during the dark ages?
Yes. I would say not during the Dark Ages specifically, because actually, let me start this over. You're absolutely right. James Webb Telescope is looking farther back in time than anything we've ever built, at least optically. The farthest back we can see anything is that cosmic microwave background. That's not picked up by James Webb because it's not designed to look for that specifically. But optically, it's looking as far back as we ever have. And you're right. There are a lot of things we're finding with James Webb Telescope right now that contradict the time limits I put here. Actually, even since I originally wrote the slides for this talk, we've discovered more that perhaps, so to give you some information, the Dark Ages, the limit I'd put on this here was it 150 million years to the first billion years? No, I'm sorry, the first 480,000 to the first 150 million years was the Dark Ages, which is defined by the fact that there wasn't any light and the stars hadn't formed yet. But what we're seeing from the James Webb Telescope is evidence that the first stars may have formed even as early as 100 million years. Now there's a lot of uncertainty about that. There's a lot of things we still need to understand to make those claims really solid. But it looks like, yeah, this timeline might be off. And what's really exciting, I'm getting really animated there. What's really exciting is that if stars were able to form 850 million years before we thought they did, we need to understand those processes a lot better. Because what we see coming out of the cosmic microwave background tells us that the density of gas clouds shouldn't have existed at that time. They shouldn't have. But if stars were actually already being born at that stage, it's going to be a revolution in understanding stellar formation, and nuclear astrophysics is going to have to lead that way. So James Webb has given us that breadcrumb. We now have to follow it. So it's experiments exactly like CASPAR that are helping us understand why that happened. For those who couldn't pick that up, you're asking, there have been no identifiable processes that have been identified thus far that can explain it. Not to my knowledge, but I admit I've not delved that deeply into that yet. But yeah, as far as I know, we don't have any theories as to why that could have happened. No.
We probably have time for one more question. I've got a microphone that works here. Here we go, Terry.
Hey, how's it going? Can you hear me?
Yes.
Okay. Could you speak to the roadmap for like the experiment for the short term, the midterm, and I mean maybe even further out? And if you could think of any maybe curveballs that would change what you're going to look into in the future if you discover it in the mid or short?
Yeah, so short term, we have a whole bunch of reactions already lined up that we want to take a look at and try to understand better. Most of the ones we have coming up right now are refinements of measurements that exist and largely ones that have been extrapolated down to lower energies before, but because they've never been observed actually inside that gamma window, we can't say for certain that those are very good. And that's really where CASPAR shines, is looking at that stuff that no one else can really look at directly. So most of our upcoming experiments are focused specifically on that. We do have, so the curveball, I'll answer that part right away. The curveball in any science project is usually the funding. And CASPAR's on the National Science Foundation. That's where we get our funding. And I think those funding cycles are probably shorter usually than most funding cycles. And I'll admit, this is not, I don't work in this part of the experiment. I work in the pushing the broom and then hopefully making the accelerator run side of things. So I've not like written a lot of proposals or interacted with the NSF, but I can tell you that the curveballs are usually funding related. And then of course, sometimes, it has another experiment already improved on this or done this thing that we want to do. That doesn't come up as often because again, we fill this really unique niche in the field. But the curveball is usually funding. If we can eventually get the funding approved for it, I think the goal is to turn CASPAR into a larger larger is not quite the word, a more complex experiment where we're able to, instead of just shooting particles at a single stationary target, have the ability to shoot particles from two different accelerators at each other, a heavy ion collider. And that's the sort of thing that would help us explore different types of reactions that are not currently open to us. But I don't know, I'll admit I've not paid attention to the proposals for that sort of thing. So at the moment, I don't know. I feel like I've done a really poor job of answering that. There's a lot of I don't knows in there, but in fairness, there's a lot of I don't knows in here too.
Let's give Mark a round of applause for his wonderful presentation tonight. And I think if you have more questions, stick around after because we can continue the discussions here as needed. I do want to note the next Deep Talks is going to be on February 12th, if I'm not mistaken. It's two gentlemen who mined at Homestake for many, many years, Tom Regan and Dan Regan, a night with the Regan brothers. It should be a whole lot of fun. So we hope you all mark your calendars and come back out for another night on February 12th. Thank you all for a wonderful evening.